So the main reason to introduce foreign key in the SQL is to enforce this constraint. When we refer to some other attributes from another table, we need to make sure this entity will exist in this referred to table, right? So if there is a foreign key constraint on from attributes of relation R to some other primary key of relation S, in other words, we are referring to some primary keys from R to S. There may exist some violations in the running time of the system, right? Let's assume this R is a sales table we defined before, and inside it we refer this beer attribute in the R table to the name attribute inside this beer's table, right? This S table. During the running time, as we adding or deleting or updating the data we have in both R and S, we will have some violations. We're referring this attribute from R to S. And if we have an insertion or update of R, which may introduce values not found in the S, right? For example, in the sales table, we have this beer name, right? Let's assume we have bud before, and then we do some update to change this bud to bud sweet. However, bud sweet is never a beer name in the S table, in the beer's table, right? It may create some inconsistency between R and S. This is one violation which may be created. We do some updating on this R table, create some violations. At the same time, if we update this S table, delete or update some beers in the S table, which may also cause inconsistency, because we may cause some beers we refer from R to S never exist, right? Which is called a dangling reference we mentioned before, right? So during the running time of the system, we will create so many different violations for these foreign keys, and we have to enforce this foreign key always valid during the running time of the system. In other words, we need to make sure the data we refer from R to S is a real data inside S. Then how can we handle this kind of problems, that is these violations, and how to enforce these foreign key constraints? So in SQL, we have different ways to enforce this constraint. And let's assume this R relation is a sales table, right? This S is a beers table. And insert or update to a sales table that introduces a non-existing beer should be rejected, right? Because if we insert some selling records, however this beer never exists in the beers table, it should be rejected, right? In this way, we can enforce this first violation will be addressed by the first rule, right? If we change this R table, it should be rejected. However, if we do some updating, like deleting or update of beers in the beers table, I mean the second case, right? The second violations. How to handle this kind of violations? So any deletion or update to a beers table that removes a beer value found in some tuples from the sales table can be handled in different ways. We have three ways. So the first way is a default strategy. We will reject this modification as well. This is also the most simple way to handle the second type of these violations. This is one way, right? In this way, we can ensure this foreign key will always be valid during the running time, which is reject all these invalid actions. Another way we can handle is to do the cascading operations. We'll make the same changes in the sales table as well. If we have some changes in the beers table, in the S table, and we will cascade the same operation on this R table or the sales table as well. For example, if we delete some beer in the beers table, the operation we will do for the R instances will also be the same. We just delete the corresponding selling records on this deleted beers. If we update some beers in the beers table, the S table, and we decide to use a cascading strategy, then the same operation will also be applied to these beers we refer to in the sales table as well. I hope you can follow me, right? So the first strategy is default we reject all the operations for this deleting or updating for the BS table. It's very simple, right? However, this strategy can also create some problems. We cannot reject some operations, right? So cascading strategy provides us with some flexibility. If we have some deleting on the S table, the same operation will also be applied to the R table. If we do some updating on the S table, the same operation will also be applied to the R table as well. This is called cascading strategy. And the third one will be set now. It's another strategy we can use. If we do some deleting or the updating to the S table, and for corresponding tuples only refer to these attributes in the R table, we will just change them all to now. For example, if we change the beer's name in the S table, and we make this beer we refer to non-existent anymore, then we can just change this beer in the sales table to be now. So these are the actions we can take to handling the previous two violation cases. For the first case, if we do some updating on the R table, the strategy is very simple. We reject all these invalid operations. For the operation on this S table, we may have some problems. Therefore, we have three different strategies: default, cascade, and set now. And now we want to decide which strategy to take when we design the tables. In the SQL, we have to declare the strategy we plan to use for these cases.